Hello students, in my last class we tried to see the numericals related to ray optics and we did some of the numericals and we completed that ray optics chapter. Now today we will see a new chapter which is called wave optics. So wave optics is the branch of physics which deals with the wave nature of light. In our previous class we saw that corpuscular nature of light and how this ray moves, how the light moves in a straight line, all these things we studied in our previous chapter. Here we need to study the wave nature of light. Why the wave nature of light has been taken into consideration. Before that, let us see what is corpuscular theory. Corpuscular theory is put forward by Descartes and it has been developed by Newton. According to this theory, light consists of particles of various sizes, shape according to their wavelengths, and they also have some physical properties. According to this theory, each particle will have some mass and they move with some velocity v. As the light consists of a different wavelength, so it assumes that light will have different particles, different size of the particles depending upon the wavelengths. When these particles, that is corpusculars, which are said to be as corpusculars, when this corpusculars strikes at the interface, elastic collision will take place. This explains the law of reflection as well as refraction on the basis of Newton's theory. Next, so clearly and successively it explains the law of reflection as well as refraction, but there are several other phenomena such as diffraction, interference, polarization, etc., which is unable to explain by using corpuscular theory of light. That is why wave nature of light has been taken into consideration. The wave nature of light is put forward by Christian Huygens wave theory. According to this theory, a source is considered to be as a point of disturbance. This source have an energy and that energy moves in the medium in the form of waves and starts to vibrate the particles of the medium. These particles will act like a similar nature as that of the source. When we join the locus of all these points which are vibrates in same phase, we will get a geometrical structure which is said to be as wavefront. So wavefront is locus of all the points which vibrates in a same phase in the medium, and that wavefront, disturbing points acts like a original source point. Now this different particles, different points which is present on the wavefront will act like a original source and they will also produce the wave similar to the original source point. The wave envelope produced by these disturbing points which are present on the wavefront is said to be as wave envelope or wavelets. So wavelets are the separate wave packets or the waves produced by the disturbing points which is present on the wavefront that is similar to source point. When we join locus of all these wave envelopes or wavelets, we get next wavefront. The wavefront which is formed first is said to be as primary wavefront, and primary wavefront consists of several disturbing points. These several disturbing points produces their own waves similar to the original source point. When we join locus of all these wave envelopes, we get next wavefront. Once the secondary wavefront is formed, it loses its identity, its link with the primary wavefront. That means once the secondary wavefront is created, for the propagation of waves, primary wavefront do not play any role. Now the secondary wavefront which is created already, which is fresh, and that wavefront again consists of several wavefronts, these several disturbing points is similar to original source point, and they also produces their own waves similar to the source point. And when we draw locus of all that wave envelopes, we will get nest wavefront. In this way, waves propagates the energy from one point to another point in a space. Now here in time t will cover some distance, and that distance is given by x is equal to v multiplied by t, where v is the speed of light in a medium and t is the time. So the distance covered by wave depend upon the time as well as velocity, and the ray is a line that arises from the source and perpendicular to the wavefront. So a ray can be defined according to Eigenvalue theory that it is a line perpendicular to the wavefront which arises from the source point. In time t, it will cover some distance which is given by x equal to v multiplied by t. So now when the wave moves in forward direction, the previous wavefront do not have any link with the fresh formed wavefront, and fresh formed wavefront will be the source for further movement of the waves from one point to another point. Here the intensity of the wavefront is given by I proportional to a1 plus cos theta whole square. When we take theta equal to 0 degree, that is the angle between the propagation of the waves and the radius of the wavefront equal to 0. In this case we are finding I is equal to a1 plus 1 whole square, which is 4a square, that is maximum intensity. This indicates that the wave fronts or the waves which is moving in forward direction will have maximum intensity, and for backward propagation of wave, the intensity is given by again I is equal to a square 1 plus cos theta whole square. Here theta is equal to minus 180 degree. Theta is equal to 180 degree. When we substitute theta equal to 180 degree here, we get I is equal to a square bracket 1 minus 1, which is equal to 0. So the intensity formula actually developed by Kirchhoff's. So according to Kirchhoff's intensity formula, the wave that propagates in backward direction have an intensity I equal to 0. So this shows that wave always propagates in forward direction. This theory is said to be as Eigen's wave theory. Now a point source, if we have any point source produces waves which are in spherical nature. So the point source produces waves of spherical nature, spherical wavefronts, and a linear source produces waves of cylindrical nature. So here we are saying this is a linear source. The linear source produces wavefronts which are cylindrical type. So cylindrical wavefronts are formed. All the wavefronts, that is whether it is spherical wavefronts or cylindrical wavefronts, all the wavefronts turns out to be a plane wavefront when it reaches to infinite points. So the structure of plane wavefront consists of like this. So these are the plane wavefronts. So plane wavefront is a portion of cylindrical or spherical wavefronts, and all the wavefronts converts itself into plane wavefront when it reaches to infinite point. Now we will see the behavior of waves when it passes through prism first. Here a plane wavefront strikes at the prism, and the lower part of the plane wavefront strikes the prism at point Z, and till that time upper point of the wave remains in free space, that is air, and the lower part of the wave already got entered into the prism, and when it moves into the prism, I mean in the region of prism, till that time the upper part of the beam spends at outside and it covers a distance of BC in free space, and after some time it also enters, I mean the upper part also enters into the prism, and it will spend a small time compared to the lower part of the wave, that is ZY. When it comes out from the prism, the upper part again spends more distance outside of the prism compared to inward. Now here let us see the time. So the wave enters and it emerges out, so time taken by the wave remains same, that is the upper, how much time the upper part will take, same time the lower part will also has to take. So the time taken by the upper part of the wave T is given by BC divided by C plus CD divided by V plus dx divided by C, and the lower part takes the time which is given by Zy divided by V. So both the waves are, I mean the upper part as well as the lower part of the wave comes through the prism at outside, so time taken by the upper part as well as lower part must remains same. So that's why here T1 and T2 both are same, whereas the lower part spends more time within the prism, upper part of the wave spends a small time within a prism. Because of that, the speed of the lower part reduces. As a result of that, due to elastic behavior of the wave, the lower part contracts, I mean it becomes closer, whereas the upper part stretches outward. As a result of that, the beam, I mean the wave on the other side of the prism shows downward. That means it emerges in the downward direction, I mean it turns itself to the base. So this is the case of a prism, that is when a plane wavefront incident at a prism, at the other end it bends towards the normal. This explains the refraction through the prism. Now let us see the lens. Here we have two lenses, one is convex, another one is concave lens. Let us see for the case of convex lens first. For upper part of the wave, we have the time taken is given by T is equal to AB divided by C plus BC divided by V, and for middle portion it is given by T2 is equal to DE divided by V, and for last portion of the wave, that is downward portion, T3 is given by YX divided by C plus XZ divided by V. Now from the figure, the plane wavefront strikes at the lens and this waves emerges out or refracted outside. That's why the time taken by all the parts of the wave must remains same. So T1, T2, T3 all are same. The only thing is that the upper part of the wave spends less time compared to the middle part of the wave. Similarly, the lower part of the wave spends less time compared to middle part of the wave. So we find that middle part of the wave spends more time within the prism, within the lens. Because of that, upper part of the wave already got refracted out. Till that time, the middle part of the wave remains within the lens system. So and due to elastic behavior of the wave, the lower part of the wave, that means the middle part of the wave, contracts because it spends more time within the lens. Upper part of the wave expands because it spends less time within the prism. Because of this reason, the upper part as well as lower part converges, whereas middle part moves as it is. I mean, it is just like contraction and expansion of a cloth, just like means upper part got expanding and middle part got contracting a little because it spent more time within the lens. That means it is moving backward a little compared to upper as well as lower part. As a result of that, both upper part as well as lower part, middle part combines together at some point and a converging type of beams are formed here, because of which we get a pointed image for the object which is lying at the infinity. So here we are getting curve wavefronts which converges at point O. So this is the way in which the converging takes place in the case of convex lens according to wave theory. Now let us see the concave lens. Here parallel beam of a plane wavefront comes from the infinity, it strikes the lens system. Here we have concave lens. In this concave lens, the upper part as well as lower part, that is upper part AB, lower part CD, spends more time compared to the middle part of the wave. As a result of that, the middle part of the wave refracts earlier compared to upper part of the wave. Due to this and because of elastic behavior, the upper part stretches outward. As a result, we get concave surfaces, and these concave surfaces, when we expands, it appears to be producing from the point O. That means we will have the focus point at O for this concave mirror. That is the beams that the plane wavefront, upper part as well as lower part, expands. As a result of that, we get a convex surface. This convex surface appears to be getting out from the point O. That means it appears that the concave surfaces are producing from point O and it is expanding outwards. So that's why here a converging type of rays is obtained when a plane wavefront strikes at the concave lens. So due to that, we get a virtual focus here. Now let us see the behavior of waves in the case of mirrors. Here we have two mirrors, one is concave, another one is convex. Let us see for the case of concave mirror first. A plane wavefront which comes from the infinity strikes at the mirror and it reflects. The upper part of the wave strikes first and it reflects first. Similarly, the lower part of the wave will also strikes first and it reflects in the same way as like that of the upper part. Whereas the middle part of the wave spends the time before reflection till the upper part comes after reflection. As a result of that, we get a convex surface, and this convex surface appears to be ends at point O. So the rays that is obtained due to the wavefront appears to be converge at point O. Once again, we have here a concave mirror. When plane wavefront strikes at the concave mirror, the upper part of the wave strikes first and it reflects. Within that time, the middle part of the wave still remain before the reflection. I mean, it is still traveling towards the mirror. Within that time, the upper part already got reflected and the lower part is moving towards the mirror. When it reflects back, within that time the upper part already covered a distance. As a result of that, the elastic property of a wave causes the plane wavefront to form a concave surface. This concave surface, the concave wavefronts appears to converges and it ends at point O. That means all the wave fronts which is formed here appears to converge at point O. Now let us see for the case of convex mirror. Here similarly a parallel beam which consists of a plane wave from the infinity comes and falls on the convex mirror. From this convex mirror, the upper part of the wave strikes first and it reflects, whereas the lower part is also strikes at the same time. Now the middlemost part, if we see, it is seen that so before the upper as well as lower part of the wave strikes at the convex surface, the middle part strikes first than upper as well as lower. As a result, the middlemost reflects after striking at the interface, I mean the convex mirror. Within that time, the upper part as well as lower part still moving towards the mirror. So this factor and the elastic behavior of waves causes to produce a diverging type of rays which gives a convex spherical wavefronts, and this convex spherical wavefronts appears to be spreading outward, but when we produce this, I mean imaginary wavefronts appears to end at the focus point. So from this imaginary wavefronts, from this imaginary point, that is the focus point for convex mirror, a wavefront appears to start which is actually imaginary. Now let us try to understand the reflection by using Eigenvalue theory. Here a plane wavefront AE coming towards the interface. Here a first plane wavefront produces the second wavefront and second wavefront produces the third wavefront. In this way the wavefront comes towards the interface. The lower part of the wavefront strikes at point B and the upper part of the wavefront still remain in free space within that time. So when it starts to reflects from the point B, in that time the upper part of the wave covers some distance fg before reflection from the surface. So when the upper part of the wave starts to reflect from the surface, within that time the lower part of the wave already got reflected and it covered some distance BC. Now the plane wavefront AB, that means the lower part AB as well as upper part EF will remain same because a perpendicular has been drawn. So the additional distance travelled by the upper part in time t is given by fg. Similarly, the additional distance covered by the lower part of the wave is given by BC within the same time. Now we need to prove I equal to R, that is the law of reflection. So let us take distance moved by upper part, that is the additional distance moved by upper part of the wave Fg equal to time multiplied by the velocity of the wave in free space. Now imagine that velocity of light is c, so therefore the distance covered in free space is given by Fg is equal to t multiplied by c. Similarly, the additional distance covered by lower part of the wave BC is also given by T multiplied by C. Let this as equation 1 and this one as equation 2. So both the things are happening in the same time, therefore from equation 1 and equation 2 Fg can be written as equal to BC. Now consider the triangle BFG and BCG. Consider the triangle BFG and BCG. In these triangles, we have here BFG equal to BCG equal to 90 degree. So the angle BFG equal to BCG, both are 90 degree because the perpendicular has been drawn. Now, the line segment BG appears to be common. BG equal to BG common. Also, we just proved that FG equal to BC. FG equal to BC. So from this data, we can say that the triangle BFG congruent to triangle BCG. Therefore, triangle BFG congruent to triangle BCG. So from which we are getting that FBG equal to BCG, that is FBG angle FBG equal to angle BGC, corresponding parts of congruent triangle. So here it is, by RHS both are congruent. So we are getting that FBG is equal to BGC, that is I equal to R. So this proves that the law of reflection. Now let us see the refraction through a surface. Here we have two mediums, medium 1 and medium 2. A plane wavefront comes from the infinity, strikes at the interface. Here at point C, the lower part strikes first. Within the same time, the upper part remain in the same medium and it is still travelling a distance dy. Within that time, the lower part already entered into the second medium and it travels a distance Cx. Therefore, the distance covered by the upper part within a free space is given by dy is equal to t multiplied by the velocity of a light in free space I am taking here as c, and the distance travelled by light within the denser medium, that is Cx is equal to t multiplied by v. Suppose that medium 2 is denser medium and medium 1 is rarer medium. Here we have a perpendicular has been drawn. Let us suppose that this angle is theta. I plus theta is equal to 90 degree, and also theta plus let us say this is alpha. Theta plus alpha equal to 90 degree. Therefore, I will be equal to alpha. That's why this angle is equal to alpha. Now come back to the downward. Here you have this angle as r. Let us suppose this angle is equal to beta. From the geometry, r plus beta is equal to 90 degree, and also let us say this angle is equal to pi. Pi plus beta is equal to 90 degree, from which we are getting pi is equal to r. So in this way, within a given triangles, we got I as well as r. Now we also calculated the additional distance moved by the upper part within a free space and the additional distance covered by the lower part within a medium. Now from the triangle, find out the value of sin I and sin r. Sin I from the triangle DCY is given by, from triangle DCY is given by sin I is equal to opposite side by hypotenuse, which is given by dy divided by cy. Similarly, sin r is equal to, from the other triangle, that is CXY, sin r is given by opposite side, which is given by Cx divided by Cy. Now we already calculated, we already determined the value of dy, which is equal to t multiplied by c. So in place of dy we can put t into c. Here you get t multiplied by velocity of a light c divided by the distance cy. Similarly, Cx we already determined, which is given by t multiplied by v. So here we can put t multiplied by v divided by cy. Now take the ratios. Sin I by sin r comes out to be t multiplied by c divided by cy multiplied by Cy divided by T multiplied by V. Cy get cancel and T also cancels. You get sin I by sin R equal to C by V, which is equal to mu 2 by mu 1 or equal to mu. This is called Snell's law. So in this way we proved Snell's law, which is applicable for the law of reflection, that is law of refraction. For the case of refraction, sine of angle of incidence to the ratio of sine of angle of refraction will be equal to refractive index of the second medium. So it is refractive index of first medium as mu1 and refractive index of second medium mu2. So these are the few topics we studied from the wave optics. I hope that you all do practice, and we will do some of the other topics in our next class. Till then, thank you.